Imagine you have designed a brand new electronic support measures ESM system for an aircraft. How do you know it can accurately detect enemy radars while flying at high speed? You cannot simply test it inside a laboratory. It must be tested in real flight conditions. In this video, we'll explore how airborne ESM systems are flight tested, why the clover leaf flight path is considered the best testing pattern, and how engineers analyze flight data to validate system performance. An electronic support measures or ESM system is a passive electronic warfare system. Instead of transmitting signals like radar, it simply listens to electromagnetic emissions from enemy radars and communication systems. Its main functions are: detect radar signals, identify the radar type, measure the direction of arrival, estimate the emitter location, warn the pilot about threats, improve battlefield situational awareness. Modern airborne ESM systems operate over a very wide frequency range and are installed on fighter aircraft, helicopters, surveillance aircraft, and EWCI platforms. Why flight testing is necessary? Testing inside a laboratory is not enough. Real flight introduces many challenges, such as aircraft movement, multiple radar emitters, signal reflections, Doppler effects, aircraft vibration, electromagnetic interference. Flight testing verifies whether the ESM system can perform accurately under real operational conditions. Flight testing validates detection range, signal identification, direction finding accuracy, emitter location, threat warning, system integration, overall operational performance. Pre-flight testing. Before takeoff, engineers perform several ground tests. These include built-in test, BIT, hardware health check, software verification, mission library loading, antenna testing, receiver calibration, interface testing with aircraft avionics, operator display verification. These checks reduce the risk of failure during expensive flight trials. Different flight paths. The paper compares several flight patterns used during testing. Straight flight, used for baseline measurements and long-range testing. Circular flight, provides continuous observation around the target. Useful for surveillance and continuous signal collection. Racetrack pattern, consists of two long straight legs connected by turns. Provides longer observation time. Spiral pattern, aircraft gradually moves toward or away from the emitter. Useful for threat assessment. Clover leaf or figure 8 pattern. This is the highlight of the paper. Why the clover leaf pattern is best. The authors recommend the clover leaf flight path as the most effective pattern for airborne ESM testing. Why? Because the aircraft approaches the emitter from multiple directions. This helps validate front antennas, rear antennas, left side antennas, right side antennas. Each direction provides different signal geometry. The aircraft performs repeated turns, creating multiple straight legs. Benefits include better direction finding accuracy, improved emitter localization, testing all antenna sectors equally, better triangulation, more realistic operational conditions. An 8-leaf clover pattern provides even better coverage than the traditional 4-leaf pattern. Post-mission data analysis. After landing, engineers analyze the recorded data. The ESM system stores Pearl's descriptor words, PDW, IAQ data, track data. Engineers then generate graphs showing frequency versus time, direction of arrival versus time, pulse width versus time, pulse repetition frequency versus time, aircraft heading versus time. These plots help identify measurement errors, signal instability, and overall system performance. Success criteria. According to the paper, an ESM system should meet several performance requirements. Typical values include detect over 90% of expected targets, identification accuracy greater than 95%, bearing accuracy within specified limits, false alarm rate below the acceptable threshold, threat warning generated within about 2 seconds, reliable operation in dense electromagnetic environments. Only after satisfying these criteria is the system considered operationally ready. Conclusion. The main takeaway from this paper is that flight testing is just as important as system design. Among all flight patterns, the clover-leaf flight path provides the best balance of direction finding, emitter localization, and complete antenna coverage. The authors also suggest that future flight testing can become more efficient by using artificial intelligence, digital twins, and advanced simulations, reducing testing costs while improving performance validation. This content is sourced from research paper P. Tripathi, V.K. Pandey, R.K. Singh, and R.R. Sharma, Optimized Flight Testing of Airborne ESM Systems for Enhanced Efficiency and Performance Validation in Proceedings of the 7th International Conference on Electronic Warfare, EWCI 2026.